In the mid-1960s, the General Electric U25C represented everything modern about American railroading. It was powerful. It was efficient. It incorporated electrical systems that were genuinely ahead of their time. And yet, across yards from Pennsylvania to California, these locomotives sat motionless for weeks, sometimes months, waiting for parts. Not because they were broken beyond repair, not because the parts were impossible to manufacture, but because the parts simply were not there when they were needed. This is the story of how a locomotive outran the supply chain that was supposed to keep it running, and how that gap between innovation and infrastructure nearly derailed one of the most important competitive challenges in American diesel history. To understand what happened with the U25C, you need to understand the position General Electric found itself in during the early 1960s. For decades, the American locomotive market had been dominated by two names: Electromotive, division of General Motors, and the American Locomotive Company, known as ALCO. EMD held the commanding position. Their locomotives were everywhere. Their parts were everywhere. Their service network stretched across the continent. ALCO maintained a respectable second place, particularly with railroads that valued raw pulling power and were willing to accept somewhat higher maintenance requirements. General Electric had been in the locomotive business for years, but primarily as a supplier of electrical components to other builders, including ALCO. They manufactured traction motors, generators, and control systems. They knew the electrical side of locomotives intimately. What they had not done was build complete road locomotives for the American market. That changed in 1960 with the introduction of the U25B, a four-axle road switcher that produced 2,500 horsepower. The designation told you what you needed to know. U for universal, 25 for the horsepower rating in hundreds. B for the four-axle truck configuration. The U25B was not merely competitive, it was genuinely innovative. GE had taken a different approach to locomotive design than EMD or ALCO, and in several respects, that approach produced better results. The electrical systems were more sophisticated, the fuel efficiency was notably improved. The overall design philosophy emphasized maintainability and modularity in ways that the competition had not fully embraced. Railroads noticed. After years of what had become almost a default purchasing pattern favoring EMD, suddenly there was a genuine alternative worth considering. The U25B sold well enough that GE recognized they had a real opportunity to challenge EMD's dominance. The U25C followed in 1963. The C designation indicated six-axle trucks, which meant this was a locomotive designed for heavy freight service. Six axles distributed the weight more effectively, allowing for higher tractive effort without exceeding axle load limits. For railroads, hauling coal, ore, or heavy manifest freight over grades, the six-axle configuration was increasingly essential. The U25C offered 2,500 horsepower like its four-axle sibling, but the additional axles gave it superior adhesion and pulling capability. It was aimed squarely at the heavy haul market where EMD's SD24 and the newer SD35 were competing. Major railroads placed orders. The Pennsylvania Railroad, one of the largest and most influential carriers in the country, bought U25Cs. So did the Southern Pacific, the Atlantic Coast Line, and others. GE had successfully forced its way into the mainline diesel market, but GE had moved fast, perhaps too fast, in their urgency to capitalize on the U25B's success and establish themselves as a serious competitor. They had prioritized one thing above all others: getting locomotives out the door. What they had not prioritized, at least not with the same intensity, was building the support infrastructure those locomotives would require. Before we continue, if you think our content is unique and informative, please leave a like and subscribe. It really helps support the channel. Also, make sure to share the video with other train fanatics out there. The U25C was not simply an EMD locomotive with a GE nameplate. It was a fundamentally different machine, built around fundamentally different components. The heart of the locomotive was the FDL-16 prime mover. This was a 16-cylinder diesel engine designed and manufactured by GE specifically for locomotive service. It was not a modified marine engine or an adaptation of something built for another purpose. It was purpose-built, and it incorporated GE's own engineering philosophy. The FDL designation stood for four-cycle diesel locomotive. The engine used a different combustion cycle than EMD's two-stroke 567 and 645 series engines. Four-stroke diesels generally offered better fuel efficiency and cleaner combustion, though they were typically more complex. Mechanically, the electrical systems were entirely GE designs. The main generator, the traction motors, the auxiliary systems, the control cabinets, all of it came from GE's own engineering and manufacturing operations. This was not a locomotive assembled from industry-standard components sourced from multiple suppliers. It was an integrated GE product. This integration had real advantages. Because GE controlled the entire electrical system, they could optimize the interaction between components in ways that were difficult when using equipment from multiple manufacturers. The result was a locomotive that, when operating correctly, delivered impressive performance. But this integration also created a dependency that would prove problematic. Consider what happened when an EMD locomotive needed a replacement part. The railroads had been operating EMD equipment for 20 years by the time the U25C appeared. Parts were stockpiled in railroad shops across the country. Third-party suppliers manufactured compatible components. Regional distributors maintained inventory. If a railroad needed a traction motor brush holder, or a governor component or an air compressor part for an EMD locomotive, obtaining it was rarely a significant challenge. The parts ecosystem for EMD equipment had developed organically over 2 decades. It was not planned from the beginning. It grew because EMD sold thousands of locomotives, and supplying parts for those locomotives became a profitable business for dozens of companies. GE had no such ecosystem. They had sold traction motors and generators to Alco and others. But the complete locomotive was new territory. The FDL engine was new. The control systems were new. The specific configurations of dozens of minor components were new. When railroads ordered U25Cs, they assumed the parts supply would simply materialize. This assumption was not unreasonable from their perspective. They were accustomed to a mature market where parts availability was rarely a crisis-level concern. They did not fully appreciate that GE was essentially starting from zero and building a support network for complete locomotives. GE, for their part, understood the challenge in theory, but their immediate priority was production. Every locomotive shipped was revenue. Every locomotive delayed was a missed opportunity to build market share. The pressure to deliver units pushed parts support down the priority list. The problem was not that GE could not manufacture spare parts. They absolutely could. The same facilities that produced components for new locomotives could produce replacement components. The problem was timing, quantity, and geography. When you build a new locomotive, you manufacture the parts as part of the assembly process. They flow directly from production into the completed machine. The logistics are straightforward because everything is happening in one place, coordinated as part of a single manufacturing operation. Spare parts are different. They need to be manufactured in anticipation of future demand, stored somewhere accessible, and shipped when needed. This requires forecasting what will break and when, maintaining inventory across multiple locations, and establishing distribution networks that can deliver parts quickly. GE had not built this infrastructure. Their initial spare parts inventory was minimal. Parts were manufactured at their primary facilities in Erie, Pennsylvania, and shipped as needed. There were no regional warehouses. There were no stockpiles at strategic locations around the country. For a railroad in Pennsylvania, this might be merely inconvenient. Erie was not that far away. But for a railroad in California or Texas, a part shipping from Erie meant days of transit time before it even arrived, assuming the part was in stock and could be shipped immediately. And often, parts were not in stock. GE's production priority was new locomotives, not spare components. When manufacturing capacity was constrained, new builds took precedence. This made sense from a sales perspective. You could not sell spare parts to customers who had not bought the locomotives yet, but it created cascading problems for the customers who had already purchased. The components that caused the most difficulty were not the large, expensive items you might expect. A failed traction motor was a significant repair, but traction motors were tracked carefully, and railroads typically maintained some reserve capacity for major component failures. The real problems came from smaller, less glamorous parts, specialized bearings that were not interchangeable with anything else in the railroad's inventory. Control relays built to GE specifications that could not be substituted with standard electrical components. voltage regulators, contactors, and switches that were unique to the GE system. These were parts that might cost a few dollars or a few $100s, but without them, a locomotive representing hundreds of thousands of dollars in investment sat useless. One of the particular challenges was the control system architecture. GE's electrical controls were more advanced than what most railroads were accustomed to, but that advancement came with complexity. When something in the control system failed, diagnosing the problem often required specialized knowledge, and fixing it required specific parts that could not be improvised. The result was locomotives sidelined for components that would, a few years later, be considered routine maintenance items. But in 1964 or 1965, those components might as well have been unobtainable. Railroad maintenance culture had developed around a fundamental assumption: you can get the parts you need. When an EMD locomotive came into the shop with a problem, the standard approach was straightforward: diagnose the issue, pull the failed component, install a replacement, and return the unit to service. The failed component would be rebuilt and added back to the spare parts inventory, ready for the next time it was needed. This swap and repair approach kept locomotives in service. Time in the shop was minimized because you were not waiting for a part to be repaired before the locomotive could return to work. You were swapping, returning the unit to productive use, and repairing the removed component at your own pace. The system depended on having spare parts available, and for EMD equipment, they were. For the U25C, the swap approach foundered on a simple problem: there was nothing to swap in. If your one good control relay failed, and you had no spare, and could not obtain one, the locomotive sat. Cannibalization was the traditional fallback when spare parts were unavailable. Take a functioning part from one locomotive to repair another, prioritizing which units were most needed. Railroads did this routinely. It was not ideal, but it kept the most critical power operating. But cannibalization requires donor units. And for most railroads, U25C fleets were small. If you had purchased 4 or 6 U25Cs and they were all relatively new, there was no worn-out unit sitting in the deadline that could be stripped for parts. Every unit was needed. Every unit was relatively new. Cannibalizing one to fix another simply created a different problem. This put mechanical officers in an impossible position. They had power on the property that should have been available for service, but could not be made available through any means at their disposal. They could not fix it with parts on hand. They could not cannibalize. They could not substitute standard components. They could only wait for GE to deliver what was needed. The frustration extended beyond the mechanical department. Operating officers who assigned power for trains faced constant uncertainty. A U25C might be serviceable today and sidelined tomorrow. Planning train assignments became more difficult because the availability of GE power was unpredictable. There is a particular kind of operational problem created by equipment that is technically available but practically unreliable. A locomotive that is definitively out of service can be planned around. You know it is not available, so you do not count on it. But a locomotive that might be available or might be sidelined for an unknown duration, waiting for an unknown part, creates uncertainty that ripples through the entire operation. Some railroads found their U25Cs spending more time waiting for parts than they spent in revenue service during certain periods. The utilization rates, which measured how effectively a locomotive was being used, were embarrassingly low compared to the EMD equipment operating alongside them. This was not because the U25C was inherently unreliable in the sense of breaking down constantly. It was because when something did fail, the recovery time was unpredictable and often extended. For railroads that had invested substantial capital in GE power, this created real operational and financial consequences. Locomotives represented major expenditures. They were supposed to be earning revenue, not sitting in yards waiting for a relay or a bearing. The railroad's initial response was improvisation. They did what they could with what they had. Some borrowed parts from GE demonstrator units that were still on the property or accessible. Demonstrators were locomotives that GE provided to railroads on a trial basis, allowing them to evaluate the equipment before committing to purchase. When a demonstrator had a part that a revenue unit needed, creative mechanical officers sometimes arranged transfers. Others worked directly with GE engineering to identify potential substitutions or workarounds. Occasionally, a standard industrial component could be adapted to serve in place of a GE-specific part, at least temporarily. This required careful evaluation to ensure the substitution would not create new problems, but desperation encouraged creativity. Some railroads simply deferred repairs, operating locomotives with minor issues that would normally have been addressed immediately. This was not ideal from a maintenance standpoint, and it risked more serious failures down the line, but it kept units in service. The strategic response was more significant. Railroads that had been considering additional GE purchases slowed their ordering. The attractive performance numbers and competitive pricing meant less if the locomotives could not be kept running reliably. Wait and see became the prevailing approach. This represented a real setback for GE's market expansion. The initial U25B success had opened doors, but the parts problems with the U25C risked closing them again. Every railroad that deferred orders was a railroad that might return to EMD by default. GE recognized the problem. To their credit, they responded. Though the response took time to implement effectively, the company began establishing regional parts depots, staging inventory at locations around the country, rather than shipping everything from Erie. They increased spare parts production, dedicating capacity specifically to support components rather than using all available manufacturing for new builds. They standardized certain components, making it easier for railroads to maintain inventory and for parts to be interchangeable across different GE locomotive models. They also improved their technical support, providing better training for railroad personnel and more responsive engineering assistance when problems arose. But all of this took time. The supply chain infrastructure that EMD had built over 20 years could not be replicated in 20 months. The improvements came gradually, and they came too late to prevent the U25C from acquiring a reputation that outlasted the problems themselves. There is a particular irony in the timing. By the middle of the 1960s, as parts availability improved, significantly, the U25C was already being superseded by newer GE models. The U28C and U30C offered more horsepower and incorporated improvements based on field experience with the earlier models. Railroads looking to purchase new GE power were interested in the current offerings, not the now middle-aged U25C. The locomotive that had struggled through its early years due to parts shortages entered its middle years, just as the support infrastructure finally matured, and then it began to be retired in favor of newer equipment. The U25C production run itself was relatively modest. Just over 100 units were built between 1963 and 1965. This limited production reflected both the transitional nature of the model and the competitive challenges GE faced in establishing itself against EMD's dominance. The U25C story offers a lesson that extends well beyond railroads. When we evaluate any piece of machinery, we tend to focus on its capabilities. How much power does it produce? How efficient is it? What can it do that competing equipment cannot? These are natural questions, and they matter. But a machine does not exist in isolation. It exists within a system that includes the people who operate it, the facilities that maintain it, and the supply chain that provides what is needed to keep it functioning. A machine is only as useful as that system allows it to be. The U25C was, by the standards of its time, an excellent locomotive. Its engineering was sound. Its performance was competitive or better. GE had produced a machine that genuinely deserved to succeed in the market, but GE had not yet produced the system needed to support that machine. And in the absence of that system, all the engineering excellence in the world could not prevent locomotives from sitting idle for want of a relay or a bearing. General Electric learned from the experience. The -7 series that emerged in the late 1970s and the subsequent -8, -9, and later models were supported by a mature parts and service network. GE established themselves as not just a locomotive manufacturer, but as a complete supplier capable of supporting their equipment throughout its service life. By the 1980s and 1990s, GE had achieved what had seemed nearly impossible in 1960, genuine competitive equality with EMD, and eventually market leadership. They did this by building locomotives that railroads wanted to buy and support systems that kept those locomotives in service. The U25C was a pioneer. It proved that GE could build competitive road power, but it also demonstrated that building the locomotive is only part of the challenge. The support ecosystem matters just as much as the machine itself. A locomotive sitting in a yard, waiting for a part that costs a few dollars, represents the same lost productivity as a locomotive that has suffered a catastrophic failure. The cause is different, but the result is identical. expensive equipment not earning its keep. This is perhaps the most enduring lesson from the U25C experience. Reliability is not just about how often something breaks. It is about how quickly it can be restored when it does break. A component failure that can be addressed in hours is a routine maintenance event. The same failure, when the part requires weeks to obtain, becomes an operational crisis. General Electric understood this eventually. The railroads that operated U25Cs understood it through direct experience, and the lesson informed how both builders and buyers approached locomotive procurement and support for decades afterward.